Hello everyone, my name is Christine and I'm representing Arnet today. Welcome on our long-awaited horticulture webinar, and today I'm not alone here. So we have here our dear friend, horticulture expert, agronom, Synergy Solutions, Andris Stuks, with me.
Hello.
Andris is here today to share the latest insights of greenhouse monitoring and how data-driven decisions can improve the daily life of any of the growers. So today I think that we will dive into various topics, touch basing aspects of climate monitoring, including the temperature, distribution in the greenhouse and how it impacts the fruit growth. Also, I think that tracking the biomass gain, if I'm not mistaken,
Yes.
Right? So plant weight and the role of electrical conductivity and irrigation topics. We will start with the presentation of Andris, and it will be followed by the Q&A session afterwards, but you can write all your questions in the chat throughout the webinar whenever it pops out. So, let's start.
Hello, my name is Andris Stuks. Today I would like you to tell and describe a little bit of what we are doing and tell what we have found out in our everyday life. A little bit about us. We are working now in 6 countries, covering more than 30 compartments. Now we have shifted our focus more to different regions, but still we are focused mainly on tomato crop, on cucumber crop. So we're working with 2 major crops, cucumber, tomato, having some insights also on lettuce and on strawberry. So what we do in everyday basis, we are monitoring plant biomass gain and climate conditions in the greenhouse. We do it mainly with Arnet sensors. So in every greenhouse with what we work, they have a set of Arnet sensors installed. I will show them later on, and I will also try to explain why they are needed and what's the benefits of having all those sensors there. If we talk why you need to add additional sensors in your greenhouse, because the concept goes as such. You have a climate computer which is steering your climate in a greenhouse. It's doing its work pretty well, so you already know what's going on. But in reality is that we know only part of what's going on in the greenhouse. We know only temperature in one spot, and most importantly, in most of the cases we don't know how the plant reacts and how it interacts with the climate. So what we need to do is we need to measure the plant responses, because at the end of the day we are selling only part of the plant, which is generative biomass, which are fruits. We don't sell leaves, unfortunately, if it's not tobacco or other crops. And so that's why we need to focus on gathering more data. So from that data, if we interpret it right, we get information. From that one further, we build our knowledge on how the crop responds to some of the climate parameters. So we have insights how those parameters are interconnected, intertwined, and from that one we can build further how to steer the crop in desired direction. So in many cases I hear the story that we don't need any sensors, we already know what to do, and that might be true with really experienced growers, but with the starting growers, the ones who start the crops and they start to grow the first time in their life, having more insight in plant responses is really good. So when we measure, usually we measure climate. So why we need to measure the climate? We need to measure what is going on in the greenhouse, what's the temperature, what's air humidity, because it has direct impact on plant responses. We need to measure all the disturbances outside and inside to steer our inside climate by influencing air temperature, air humidity. Now with the new systems of ventilation, also airflow, which affects the biomass gain and photosynthesis. So, and we need to get insights in all of it. So, and that's why I would start with climate, and I will dive a little bit deeper in climate set points versus realization in greenhouse, because when we have climate computer, we put in temperature, we put in humidity, and we hope that it is going as we expect. But there is that thing that ignorance is a bliss. As less you know, as better you sleep. When I started my career many years ago, I thought that I know everything, and I was really in peak of this mountain of stupidity. So then when I have started to measure and compare in different greenhouses what's going on, then I went through, how to say, hell of knowledge, where you understand that all your previous beliefs was wrong. So, and for that one is really important to know what is going on in your greenhouse, because usual process of plant growing is that you have your climate set points, you have your expectations how your plant will grow, how the crop should look like, but then you start to interpret it, and then you see, well, my plant is growing differently than I have been expecting. So that's why it's good to make the temperature map, because in a temperature map you can see the differences in a greenhouse on a plot of greenhouse, and you already can foresee upcoming problems like with fungal diseases if it's too humid and too cold, and with too quickly changing temperatures and humidities. So, and as example, we have a greenhouse with 7 hectares. I have nicely drawn 2 dots on a map. I will show you later on why they are there. There are 8 greenhouse climates. All the climates have the same set points. So what we expect that they will all grow the same. So the climate realization will be the same and plants will grow the same. But it turns out in reality that actually there are quite big difference in greenhouse temperature from climate to climate. And that greenhouse temperature increase also influences the plant temperature increase. On a right side graph you see the set point and ventilation, so the heating set point and ventilation set point and realized temperature. On the left side you see that so where's my pointer? It's there, and we go back to pointer. So this is climate settings and how the Priva shows the climate realization, but in reality in greenhouse you see that temperature difference is up to 4 degrees. So, and when you do the plant registration without measuring the temperature next to those plants, then you end up in a situation that you look at your plants from the plant monitoring, and there are those 2 dots what I've drawn there on the map, that in one case you have plants which are more thick, with a thicker trusses, lower growing truss, more vegetative plant, but also with not even fruit setting in on the lower trusses. And then on the right side you have a plant which is thinner, more generative. And then when you start to interpret your plant registration, it happens like in a story when 4 blind men start to describe the elephant. So it was because of the irrigation, it's because of the heating, it's because of the air exchange or screening, but actually it is because you haven't measured the climate around that plant, what you have been measuring in plant registration. So for that one, it's important to measure the climate next to the plants, which you later on want to use as a set point for the steering your climate further. Then another topic on climate uniformity. So another example in climate uniformity is 5-hectare greenhouse also, where we have noticed that there's uneven fruit ripening by time, and especially in the beginning of the crop season every year there have been corners in the greenhouse where fruits get mature like 1 week later than another part, although the plants have been sown in 1 day and everything have been done exactly the same. So what we decided there is to create a heat map. We installed 14 sensors to see how it have been going, and also there we noticed quite big differences in temperatures, so especially in the night temperature. So night temperature can vary by 5 degrees, and also minimal temperature during the night is varying by 4 degrees. So, and for that one we have found out where the cold spots are in greenhouse, and we made all the possible actions to minimize it. So, and we made it by controlling the screen gap. So the screen gap is the important tool, because I will show later on in slides, cold air, so the warm air cools down and above the screen, and then it rolls down to the coldest, to the lowest part in the greenhouse, and then it drops on plant heads. And it's also important to divide greenhouse ridge in parts, so you create smaller cold pockets, and so there is no such big influence at the end of the greenhouse. So how it looked, and what we measured is that average greenhouse temperature was different. So there have been difference up to 2 degrees in 24 average greenhouse temperature. So that means that plants in a warmer part, they have been growing quicker and faster than in another one. And also we have seen a really big difference in water pressure deficit average. So that's average 24-hour water pressure deficit. So that means the plant transpiration potential. So, and depends on the time of the day when this difference in water pressure happens. That steers your plant into too generative or too vegetative action. So you can get too fat plants or too thin plants with stretched leaves, stretched stems, and aborting fruits on the truss. So now we more and more use RTR, so radiation temperature ratio, where we have our base temperature, and especially when we grow with natural light only, we base our 24 average temperature based on light sum what we have achieved. And in this case, with measurements in the greenhouse, we see that also there the RTR is really off from compartment to compartment. But most importantly, what we have looked at was lowest temperature in the greenhouse, which have been happening for 15 minutes in a row. And there we see that in some places greenhouse temperature have been dropping up to 9 degrees, and like 9-10 degrees. And tomato chilling happens already at 10 degrees, and you can get inevitable damage on the fruits. But those temperature differences are leading to the differences in the fruit growth. So the fruit is growing based on temperature, so it ripens based on temperature, but it gains its weight based on a light sum which every individual fruit gets. So you can scan a QR code in the corner of this slide. You will get to the publication where this information is derived from. So, and those difference in the greenhouse that we have seen is actually the cause why we have different fruit ripening speed and different size of the fruits in different compartments. And that and too cold temperature what we had in the greenhouse is actually causing the fruit damage. And this fruit damage really looks like now quite popular virus what we would not like to see, the TOBRF virus. But in this case we tested it negative, but still we have this cold damage, and it should not be mistaken with TOBRF. So it's better to have a cold feed and test negative that it's not TOBRF, but it's also is better to keep your tomatoes warm and don't get them too cold to prevent this cool damage. So if you have made your heat map and if you have seen that there is differences in the greenhouse temperature from end to end of the greenhouse, you could also scan QR code on this slide, and you would be lead to the Het Nieuwe book in Dutch. So you could read that book. I would really suggest you to read it and learn it from your heart. That's the book of the basic greenhouse physics and plant responses to the greenhouse environments. But the best thing to do in this case is to divide the greenhouse ridge in multiple small pockets. So in our practice we have been dividing that one of those pockets is around 35 meters. So in this case we have seen that the greenhouse uniformity comes up from 21 to 16. That might be quite difficult, quite extreme example, but we have seen that the temperature difference from one end to another one in 24 average temperature have been from 18.5 to 18 degrees. So 24 average temperature is evening out, and the night temperatures differs by 1 degree. So that's quite simple solution what you can do. You can do it or with plastic foil or with screen leftovers, whatever. You just cut the ridge in parts, and that would do the trick for you. So my insights and takeaways, what I would like to take with you, it's just little rephrased, good phrase, is that it's better to have serenity to accept the things what you what you cannot change, and just live with them and work with your plants. And you just accept that you cannot change. Courage to change those things what you can, divide the reach, do the pruning differently in the places where it's colder or warmer. Wisdom to know the difference, analyze how do they differ, and then enough sensors to measure those differences in the greenhouse. That would be the best thing to do. So plant biomass and what we see. The plant biomass is really important tool to get you from 0 to hero. If you never have grown the plant, or you start a new crop, you start a new variety, then you should start to work with plant biomass, because there are simple ways how to get to the result in 1 year. And I would like to go briefly through the cucumber yield planning. We have done it in a greenhouse in Latvia when we started first to work with LEDs. LED is a new topic in many countries. Many companies are moving from HPS to LED, or starting from non-lit crops to lighted crops. And in this case, you would install the plant scales to monitor the plant biomass gain and plant weight. And also you could foresee the problems which would come with changes in plant weight. So usually what we start is we plan our weekly light sum. In our case, it was that we have been planning every week to have 210 moles. It will be good to ask from your seed supplier or a breeder what is the light use efficiency for the crop. Like light use efficiency here, this 22 grams per mole. It stands as light use efficiency. So that means that means how many grams of production you can use, you can grow per 1 mole of light. And it is better now to measure your light in micromoles and calculate it in moles, because different producers have different light outputs, and it's not anymore enough to measure it in watts, and it's not also wise to express it in joules. So when you know your light sum, when you know your light use efficiency, you go to your calculation. In our case, it was that we planned that we can have minimum 4.6 kilos per square meter per week. From that one, we have calculated how many fruits we should keep on a plant. So in our case, it was because we are limited on fruit size is 250 grams. So that's why we can keep 18 fruits on plant. That means that if we have 3.56 plants, that's our planting density, we should keep minimum 5 fruits per week. And because our plant is growing 6 leaves per week, that means our pruning strategy should be 5 fruits in, 1 fruit out. And from that one is that our fruit load shouldn't be more than 12 fruits. And that means that every week we should add 5 fruits on the plant. So that means by pruning we remove 1, so 5 fruits are added, and we harvest 5 fruits. So from that one we know what should be our average plant load of fruits. Last year we made the measurements of every fruit on a plant for whole months, in months of April and May. So the graph what you see here, that's measurement of fruit day per day, and you should look at this fruit in that day is that fruit on that day. So from that one we can calculate what is our average fruit weight on a plant. So this have been always measured before harvesting. So knowing how many fruits you add and how much you take them off, you know also in how many days they should grow. So that is also determining your fruit load. That is determining your fruit weight on the plant. We have been measuring also every leaf on a plant, so then we know what is the allowed leaf weight on a plant. So we measured leaf blade and leaf petiole. We came to that weight, and as every week we add 6 leaves in the head of the plant, we remove 6 leaves from the bottom of the plant. So then we know what should be our actual plant load. So that we know that every individual plant can be from 1.3 kilo to 1.7 kilo. which means that from that one we also could know how much weight we should see on a scale, so we know how many scales there are. What you should keep in mind that leaf weight is really variety dependent. If you want to grow based on biomass gain, you should do some homework on measuring your plant which is growing. You can just disassemble piece by piece, write down every fruit position, every fruit weight, every leaf position, every leaf weight, and then from that one you can calculate what would be the normal plant weight. And then you will have your guidelines for the plant weight. And when you grow your plant, or if you have grown it, let's say, for a few weeks, then you do plant biomass distribution calculation, and that we have done by every time when we have harvested fruit, we write it down as the fruit harvest. When we have harvested leaf, we write it down as a leaf harvest. From that one, we know our biomass distribution in plant fresh weight biomass distribution in fruit or leaf. That is necessary to determine your maximum and minimum plant weight, what you should see on a scale, because if your plant grows, so if you have higher plant weight on the scales than it should be by your good calculation, that means that you have cucumber fruits which are not growing at the pace as they should be growing, and you have risk of fruit abortion, and you basically have useless weight which is not growing efficiently enough. And if it's too low, then you don't have enough fruit load. And if you have enough plants on the scale, or you have more than one scale in the greenhouse, then you also can see the differences in the biomass gain per different climates. And always you can recalculate this biomass gain in grams per mole on a daily base growth. So, and as a result, from all those measurements, as we are monitoring plant weight over the period of time, we know the time delta, and then we sum it up, and then we have biomass gain per day. And then, because in the previous slide I showed you the biomass distribution in fruits, if I know my biomass gain per unit of area, like I have gained here 820 grams per square meter per day, then my weekly yield should be around 4.8 kilos, because in 7 days I will get 5.7 kilos of total biomass, and from that 85% will be harvested as a fruit. So I have already possibility to check whether I will fulfill my yield prognosis. So it's already like alarming me if I have too low plant weight, there's not enough biomass gain, I will not get my fruits. So we started this growing with the scales in Latvia in 2019. 2018 was total failure when we switched to LEDs. We harvested only 123 kilos from promised 165. In 2019 we learned the first tricks on how to use the scales. So in the first crop we were learning what to do. On the second part we were already knowing what we are doing. And then in 2019 we actually went above the promised light use efficiency, above the promised kilos by the LED producer. And there the things that we learned was that air movement is important if you have LEDs, and if you grow your cucumber with LEDs, because the because the lamps doesn't produce so much heat, you need or heat more, which is lowering relative humidity, or you need to move the air around to pull the water away from the leaf, so you need to decrease the leaf boundary layer. And since we started to use our air circulation system, we have air and energy system there, we started to get more transpiration and more photosynthesis and more biomass gain. We have started to plan, so we have been planning our yield based on light use efficiency, how many fruits we need to have. We have been looking, okay, now the plant weight is too low, there's not enough biomass gain. So for sensors, what you can use for plant biomass monitoring, so those ones are definitely must-haves. If you start the new crop or you start a new variety, all those sensors make perfect sense why to use them. Like now we widely use Subflow measurement kit. We will have a presentation about it later. Now we do it on tomato, water in, water out. We also have some slides about it later on. Also stem diameter is a good sensor to use, because that one is showing you how much your water is suffering the stress. I will touch that one also later. So the weight is a must-have at every greenhouse. PAR sensor is definitely must-have. EC will help you understand how your plant takes up the water, or it's because it's not available, or because EC is too high. Plant temperature sensor will allow you to see the water pressure deficit. So that's between how much there is water pressure deficit in so the saturation pressure of the air and saturation pressure of the plant. So that's the plant, how good it is cooling itself. So all those sensors have a perfect sense. And so the plant weight, as I already mentioned, is the most valuable tool to have. And we are harvesting only part of the biomass, that's fruit, and we're always trying to maximize the fruit gain. And we are also, if the plant stops to grow, then mostly this biomass gain decrease is because the fruit is not growing, because it makes the major part of the total biomass gain. So you should look at it carefully. There are ways how to interpret biomass. So far, until 2020, we have been looking at the biomass as cumulative biomass gain per day, which is also a good tool to monitor it, but you may miss out some details. We have a good example of bad examples. We have greenhouse which doesn't follow our strategy. We have a changing plant temperature, air temperature, and water and air humidity. So definitely there are climate computers which are better than others. So, and for that one we came to the new way of interpretation of biomass, and that is interpretation in a biomass change, biomass gain per unit of time. So in this case, just a little bit explaining what it is. If we take all time at which we are looking at the plant growth, we take the plant average weight, we take biomass gain per day, and we calculate the average biomass gain per unit of biomass. So that's like, if you take the loan, that's interest on principal. You have some money what you have taken from the bank, and you need to pay every month some interest on it. So that's the same. You have, let's say, 20 kilos of plants per scale, and from that one you're getting 20% per day. And what we are looking now at is how does the biomass gain is changing per day, per change in humidity. I would really appreciate if you will write later on the questions, and most probably you will have questions about this graph. It is quite a busy graph, but basically what it says is that when you have changing air humidity, your biomass is fluctuating with it. So there are moments when your plant is drying out, so you go below those 20% what you have been normally getting per day, and you are later on pushing the water in, which is also not good. So the best way how to grow is that it's a stable biomass gain with less changes. Also, by interpreting per unit of time, you also see that where you are temperature limited or where you are humidity limited. Like you see that in the morning the humidity deficit is lower, that's why the biomass gain is higher. In the afternoon, at the same light conditions, the humidity deficit is higher, but the plant biomass gain at the same temperature, at the same light intensity, but at a changed humidity deficit is actually lower. So also there you see that, yeah, humidity is a driving force for the plant gain, and especially it's visible in the next day. In the morning, humidity deficit low, biomass gain high. In the afternoon, same amount of light, humidity deficit high, biomass gain lower. So it's better to look at the biomass gain and the plant growth as change per unit of time, per unit of other parameters. So where the stem diameter plays a crucial role. If you go with plant weight only, and the green graph here represents the plant weight. So then when the sun comes out, and especially I made this graph a little bit smaller in scale, so when sun comes out and there's around 600 watts per square meter, you see that at the peak of the day, at some moment of time, the biomass stops increasing, and so there is a drop in biomass. And also at the same time, if you measure the stem diameter, then you can explain why it is decreasing. And usually it would be that if you see that that plant biomass is decreasing, so that means that we are losing water from the leaf. So leaf is losing tugor. If you couple your setup, sensor setup with thermal camera or with visual camera, you would see that your leaves are sagging down. So they're losing tugor, so they are kind of not wilting, but just bending down. But then when you start to see that the stem diameter is decreasing, that's already the sign that you need to shade, because that is meaning that you are losing water from inner buffer in the plant. So because the plant have outer layer, and then inside you have this, in tomato plant you have this white spongy stuff which is filled with water, so it's the plant internal water buffer. So if the stem diameter increases, that means the plant is missing water. So it's not critical, but that means that in the plants which are already weaker, they will get even more weaker. And then you see that in an afternoon when the sun goes down and when the water pressure deficit decreases, then you see that plant is regaining its diameter and the reserves are filled up. Then also by stem diameter you could see in afternoon if there is a excessive spike in a stem diameter when the humidity deficit is going down or you're cooling down too quickly. So that is the moments when you're making overpressure in a plant, and we have linked this overpressure with the blossom and rot appearance and with grey wall. So mostly after those periods when we had uneven climate with uneven biomass gain and stem diameters, it happens at truss number 3 and 4. You see that there is where your those fruit problems start to form, like blossom and rot and grey wall. So moving forward, I already mentioned to you about Subflow sensors, what we have been using now. Then sorry for a busy graph, I have been famous for too busy graphs and too difficult to understand, but that's not my problem. That's your problem that you don't understand, right? So temperature and subflow in the top truss. So if you draw the plant, it have many leaves, and then usually we have trusses until we have leaves until truss number 6, and now we are measuring top leaf, so which is or directly below the flowering truss or a little bit above the flowering truss. That's the subflow. Which one it is? Yeah, that's the subflow to the leaf, and that's the subflow out from the leaf. So this is net radiation, so we are measuring radiation on top of the plant, so incoming and outgoing radiation. And there we see that during the night, so when we have or 0, a little bit below 0 net radiation, so that means the plant is losing the energy. The subflow to the leaf and out of the leaf is close to each other, so that means that there is little transpiration, and most of the water which comes into the plant is going out of the plant, so we are doing the unloading from the top leaf. But then as soon as we turn the lights on, and here you see this famous spike of turning LEDs on, that first it starts at high intensity and it drops down, so at that moment plant takes more water to the leaf, but there is less transpiration out of the leaf. So, and by measuring the subflow in your plant, at the head of the plant, you could nicely explain at which moment your leaf to burn happens. But because we have found out that this leaf to burn, what you have, it's mostly in the morning time when you switch from night, from the high humidity or low humidity deficit to high temperature, high transpiration, and plant needs to transpirate, but there's nothing to transpirate because it haven't been taking water up whole night. And then during the day, when you see the temperature fluctuations, you also see that the plant is following, so the leaf is following the trend. And as water is going in the leaf, if you take the average, every fluctuation which is going in the leaf and which cannot be transpirated is actually expressed as the water which is coming out from the leaf, so that you also can take as a fluctuations in the pressure in the plant. Then in the morning, which is also good to see with this net radiation measurement, is that when you open the screen, if you open your screen too early, so actually this net change in radiation is also changing the water flow. So basically, because the plant is now losing the energy, somehow it's also less, taking less water up. So there is a nice dip in water uptake. If we go to what happens in the middle of the plant, same plant, only different leaf. It's a middle layer where there is less influence of the light. Same temperature, same everything, and there we should go to subflow in the truss and subflow out from the truss. And I have made them a little bit wider so you can see what's going on there. So this one is this one have less fluctuations by the temperature because there are also less influences of radiation. So incoming subflow is changing, but it's actually more influenced by the transpiration than by the water which is coming in. So if there is change in water in air humidity, the plant is transpirating more. The water transport to the leaf is more or less the same. But then on the bottom leaf, it is that it is more related to the temperature, and it is also related because we are cooling down, we are heating up with the heating pipes, and that leaf is actually more following, so the subflow in the middle leaf is more following the air temperature because it is most isolated of the light. So that leaf gets around 20 micromoles of light in average per leaf blade, so there is no influence of fluctuations in the light some, but there's more influence in fluctuations in humidity. But think about the topic about the subflow. We should make another webinar and tell about it a little bit more. So the role of EC, I have been already showing those slides in previous presentations, but they are good slides, and why should I look for new ones because they are happening and again. This is already prepared. So the measurements we have made with EC increase in period of time, we see that our biomass decrease in, so we have decreased increase of biomass. So if we zoom in this period of time, so when EC have been increased, we see that before increase, the biomass gain have been happening flat. There have been no changes in stem diameter. The biomass have been increasing flat, and every irrigation didn't make any difference. But at high EC, when substrate was already EC of 6, and we have been irrigating with 3.1, well, where delta was above 1 EC, which is already bad. We have seen that there have been a lot of fluctuations in biomass gain, and that is it real deal that it is affecting the pressure in the plant. You see that increases in plant weight, the rapid increase, what we see here, is also coupled with the changes in stem diameter. So if you see that also your stem gets pumped up, this is the moment when you create a pressure in the plant, and as a consequence, after 5 weeks after this accident, we had a gravel, more expressed gravel on tomato fruits. So I would really watch out for it. You can see it already on plant scales, but if you have the stem diameter, you have nice coupling of what's happening in a plant. So after we have decreased EC, we have seen that. So since we have an increase, we have seen that also the biomass gain have increased. So we have been missing out the biomass increase over the night when the EC was the highest. Still, there happened the transpiration because of because we are heating. That was winter time, and since we decreased EC, since we increased the water availability for the plant, also biomass increased. And if you express in regular numbers, those 60 grams of biomass increase per square meter calculated over 75%, which minimal goes in fruits for tomato. Let's say you have 10-hectare greenhouse, that comes in a quite hefty sum. And with preventing second-class tomatoes in one event, you already pay back all of your sensors. But bad habits die hard, and the same customer, different year, same problem. That requires to have attention on what you are doing. Also here we see that EC continues to increase day by day, and you start to see again the same nice pattern of biomass increase at every irrigation. But now we already know that we need to act fast. And in this case, if you see that EC increase is happening, then the best case is to lose a little bit money during the day, if you can, and irrigate with more excessive drain during the sun when you cannot harm your plant because the plant is transpirating a lot, and in this moment you can change your EC in the substrate. So that would be the best strategy to flush when you have a lot of light. So when there is sun, there is more transpiration, that's the perfect time for flushing the substrate. And then about the light. So basically what we are doing and who we are, all of us who are listening this presentation, the ones who are speaking, we are conversion of the sun, we are conversion of the free available energy, and this is also what we are doing in the greenhouse. We are converting light into something that we can eat or something that we can give as a present to others. And we go to light measurements. So it is important to measure light with more than one sensor. And the minimum sensors what I would recommend to use in greenhouse, if you measure inside of the greenhouse, would be not less than 4. And you should be measuring in multiple places, because otherwise you can be fooled by the amount of light what you have. Because in this case, what you see in this example, it have been sunny day which turned in a cloudy day. Sensors in the greenhouse are placed in a grid pattern. If we have a greenhouse which is 4.5 meter wide, the post distance is 4.5, it's 8 meters wide, and there have been 4 rows in the greenhouse. Then we have placed our sensors above every row in diagonal, so we can measure above every row in different places because there is a shading of the construction. And what you see here is that one of the sensors catches light in the most periods of the day, and then there is some dips because of the construction, which is shading off the light. But many of those sensors get shaded by just by glass, because the light angle, so the angle at which light shines on the glass is also proportional to light reflection, and as lower is the angle, so as closer it is to 0, as more light you reflect and as less light gets into the greenhouse. So that's why you measure with more than one, and you take the maximum to calculate the amount which goes through the glass, and then you subtract from that the percentage which is blocked by the construction. And the amount which is blocked by construction you can calculate by just taking your greenhouse plan and counting how many structures you have there per unit of square meter, and then that will be the amount what you would lose from the construction. So another important factor is that you need to determine when to wash the roof. In our case, in the greenhouse, which is closest to me where I work constantly, we have birds which make not even whitewash on the greenhouse, and constant light measurement gives us really good starting point when to wash the roof. And just one example on how important it is to measure is that on the 30th of March in 2020, when we started to work with more than one PAR sensor, we saw that before roof washing it was 1060 micromoles, and after it was 1350. Keeping in mind that we have been measuring also artificial light. You need to keep in mind that artificial light measurement with sensors is a really bad idea inside, but that's why we have subtracted here the amount of light what we have been getting from artificial light, and actually we have been losing 26% of sunlight. So that's a lot. You can see it and you can foresee when you need to wash your roof, because 1% of light is up to 1% of production, from 0.7 to 1% in production. And then why it is bad idea to measure artificial light is because then you need to have the perfect placement. If you have your light plan and it says that you have 300 micromoles of light or 400 micromoles as in our case, you need to know exactly where to place the sensor. We have placed in above, like in around that place where we have the micromoles, but we are using that one only just to check how good our dimming is working. Is it working or is it not working? Because we have our set point at which it should be dimming, and then we see, yes, natural light have been fluctuating, but actual artificial light inside of the greenhouse, so the total light sum have been flat. And also you cannot measure interlight with your power sensor without making too many adjustments, how to put it. And most importantly, with the light sensors, trust them, but verify frequently, because they can get dirty, dust can sit on them, they can be bent, so little inclination in angle will also show you different results. And that was it. Hopefully you get something out of it. There will be a recording of this presentation, I think.
Yes,
Right.
there definitely will be a recording. We will definitely share it with everyone who has registered, and this will be also available on our ARNet YouTube channel. But thank you, Andris. I think this was very valuable insights and information to, I think, improve the daily growers' actions in the greenhouse. And if anything was not understood, you can definitely reach out to Andris, contact him personally. The contact details up on the last slide. And I think, yes, stay tuned with this information, which is, I think, a lot to learn. But we have also questions, Andris, a few of them being sent in. So in case anyone wants to ask anything also right now, you still can use the chat log for that. But yeah, the first question, Andris, is how do the ARNet drain measuring and monitoring is used?
Drain measuring and monitoring. I suppose that what it's meant with this question is how the spoon of the drain measurement is used. With that spoon, depends on specification. There can be or 10 or 5 milliliter per tick. You calculate your count of pulses with the drain, which have count of pulses with milliliters, which is coming out, and then you know the volume which have been dripping out. If you use the same sensor, the same spoon also for monitoring the irrigation, then you can nicely see how much was the irrigation, and you could calculate the drain percentage. I hope that answers the question.
Well, in case not, then additional questions welcome. The second question is, what is the optimal distance between sensors to accurately map the temperature and light distribution within a greenhouse?
Temperature, definitely not less than 1000 square meters per sensor. As more is better, but 1000 square meters would be what we have seen is really relevant and good distance. For light sensors, again, it would be good to measure only natural light, not artificial light, and then not less than 4 and equally spaced over the roof pattern of the greenhouse. And not less than 4 inside and 1 outside, just to compare how much is coming from outside to inside.
Okay. What can damage temperature and weight sensors?
Definitely it can be spraying compounds, the chemical compounds that you use for spraying for pests. Direct humidity, let's say water splashes, or being too long in too high relative humidity. If you put your electronic sensor in 100% humidity, that's already mentioned in a specification of the sensor, then it will start to drift and it can be damaged. And then we need to talk about which damage. I haven't seen, in my experience, too many sensors which have been damaged that you couldn't use them, but we have seen the temperature drift and humidity drift with the time. On weight sensors, you could see rust, but rust is an aesthetical problem, not a physical problem. It doesn't affect the reading accuracy, and you still use them. So we have the first sensors since 2018. Yeah, they look a bit worn, but that gives them nice little look. They have a little patina on them, but they still work perfectly.
There's another one. How to make sure that weight sensors are not influenced by temperature/radiation to acquire accurate measurements?
Well, that's quite easy. You place them in your environment where you're going to be measuring the weight. You block them from influence of wind or any other physical movements, vibration or others. And then you'll put static weight on them. Let's say you have 100 kilogram sensor, you put like 20 kilogram weight, the weight what you know, and then you observe over the time what's the change. So the specified change should be not more than 0.01% as far as I remember. So and then you should see whether it is affected or not.
Okay, we have a few more questions. There's a question from Sergio. What are the recommendations about Subflow sensor installation? What is the best place, bottom, mid or high, to put the Subflow sensor? And how do you measure water in, water out with Subflow sensor?
Yeah, this particular Subflow sensor is meant for small diameters. It's simple to measure the subflow on a rose. It is simple to measure subflow in a fruit. It is simple to use measure subflow in a leaf, and it is used as a clip. You put it as a clip on a place what you want to measure, and what you will see, you will not see the absolute flow. You could estimate the absolute flow. You will see the rate of change of flow, because this sensor is based on a temperature difference. And you will say, is there any difference in the subflow during the day or during the night, but not absolute volume.
Okay. We have a question from Joris. How important is the light penetration into the crop, for instance, for tomatoes? And what setup would you propose to measure this?
Well, depends on your budget. You could go in a way that you measure every 10 centimeters one sensor, but that's comes at a hefty price. But what we have been using in practice is that both in cucumber and tomato, we have a PAR sensor above the crop, and then we have put the PAR sensor in the projection of the crop wire and the crop underneath the crop. Just make sure that it's not covered with the leaves, and then we are comparing the result from the top and from the bottom. The normal light absorption should be not less than 90%, and if you see that, let's say, above you measure your artificial light of 200 micromoles, and if you see that on the floor you see around 20 micromoles, then you have sufficient leaf. If you have less than that, then you could remove more leaf. And the easiest way is to measure above the crop and directly below the crop on a projection of the vertical. So on a vertical of the crop wire underneath the crop.
Okay. There's a question from Maxim. What is optimal distance between leaf and IR sensor?
That's a good one. Definitely I suggest to use more than one sensor, but what you should keep in count that the sensor is looking at 2-degree angle. As further you go, as less certain you are which part of leaf it is measuring. I would suggest not to go more than 40 centimeters above the leaf, but also not less than 20, because of the leaf movement. The ones who have access to internet, they could see it in YouTube, how the plant is moving. In my YouTube channel we have done a lot of videos of plant movement, and there you could see that your measurement with this sensor will be most precise if it is in a range from 40 to 20 centimeters from the crop, from the leaf.
Okay, for now there are no more questions. In case you have any questions, feel free to send them in to us, to Aranet, or directly to Andris. And yes, thank you everybody. I think that we have done a great job here today, introducing these tips and tricks and a lot of insights. And in case you want to find out more, then you definitely can follow both of our social media. We are pretty active there on LinkedIn, Andris himself and Aranet, so Aranet Pro, search for it on LinkedIn. Our page is active with the content diving into a lot of horticulture topics, and stay tuned for the latest information of upcoming horticulture webinars, actually pretty near in May. So there will be a lot more news coming, and yes,
Thank you for joining us today.